Hello to everyone. So here we're gonna be showing a little bit how to align the microscope, the STEM microscope for EELS data acquisition. So since you're gonna be acquiring EELS data, it's always better to use the camera at the end of the GIF. So essentially, we're gonna be converting our EELS spectrum. Right now, you see that is in EELS mode. We switch to EFTEM mode. Now we already covered part of this lecture in a previous lecture about how to get you like nicely set up for EELS STEM, but we're gonna cover this again. Okay, so go on STEM, scan here. So we'll scan an image. We unblind the beam. Okay, so it's bright because we have a largest aperture, so you maybe want to adjust the gain of the detector. You see something there. Okay, let's focus first of all. Let's focus with the Z. Okay, very good. And now we want to look at our ronchigram. So we use the camera at the end of the GIF. So we can stop the acquisition. The beam is going where the park is selected right here. So this is a nice amorphous. You can go through focus. So as you see now that actually this ronchigram looks pretty good. So this microscope is an uncorrected microscope. But if there was some astigmatism, so I'm going to introduce some astigmatism just to give you the idea of how it should be. So I introduce some astigmatism, and now you see there are a lot of stripes here, which we have to correct. So again, the astigmatism, and you try to make circle like this. That looks very nice. Also, make sure that the ronchigram is in the center of the field of view. So go on the projector alignment or diffraction alignment, and you move this ronchigram right in the center. So in this particular moment, you see that our convergence angle, which is determined by the condenser aperture, is actually pretty large. So this is not really very good for EELS STEM. So we have to change to a smaller aperture. Okay. So you look at the ronchigram. We correct the astigmatism. Looks good. So now you could. Now we found the center of the ronchigram. So you can use either the cursor of your mouse, or you could use an object which you can access by right-click on your mouse. Okay. So you could go on here and say, okay, I want to use a rectangular. You put a rectangle. You draw a rectangular right in the box of your ronchigram right there. So now we're going to put a smaller aperture. Number 3. And we center this aperture with respect to the object right there. Okay, looks good. Let's focus again to make sure there's not much astigmatism, but looks good. And now at this point, we again make sure that the ronchigram is going in the center of the image. So with a PL, we'll move it to the center of the image like this. And now we're good to go. Very nice image. One more thing. You see that, first of all, you want to adjust the gain of your image because we changed the aperture. And now, obviously, we have a lot less intensity. So let's bump the gain again. So this looks pretty good. But you see that when we scan across the interface, the substrate is crystalline silicon. You see that it's a little bit out of zone. So you can try to tilt and make sure that it goes on zone. And let's look at. All right, looks pretty nice on focus. The only thing that you have to do is adjusting again the height of the specimen because we tilted the sample. And again, you're gone with the Z. Okay, looks really good. One more thing. You could go on focus loop, and you can place the focus loop across an area of interest here. And you can change with the arrow key. You can change the number of pixels inside, right or left. So we are increasing the number of pixels, or you can also increase the dwell time going up or down. Okay. So the image looks pretty good, and now we can do some mild, some fine focusing. It's getting worse. Now looks pretty good. Got a very nice image. Let's go on preview. Always make sure that the park is like sitting on vacuum if possible. So the beam, when we stop the acquisition, the beam will go right there. And with this, it's all. Okay. All right, I think we are ready to start the acquisition. So we stop the camera and now we are ready to switch to EELS. So now we're gonna convert this gram to an EELS spectrum. So we're showing you how to align the aperture, change the aperture, align the aperture, make sure that your probe is smaller than, so basically your convergence angle is smaller than the aperture. Also, another thing that you should consider is your convergence angle. So normally the convergence angle is just the half distance of the diameter of the probe. So you see this is the probe here. So we already measured this and we found that our convergence angle is 10 milliradians. So the distance, the diameter of this probe, this circle should be 10 milliradians. So we can check that. So right click. And we just took a line. And it's about 20. So it shows the alignment is actually pretty good. Okay. So we switch to EELS, so we can actually close the image now, the probe. Now we converted that probe to an image. So first of all, we want to make sure to focus the zero peak. So you type on the energy 0, and you can decrease the acquisition time. You can go on view. You see the spectrum is nicely here centered. You can go on align zero peak to make sure that the beam, the zero peak is right in the center. So you can stop the scanning and perhaps move the beam to vacuum, and you can actually perform, you can focus zero peak automatically. So you see the light here is amber, meaning that it might require some focusing. So you go on autofocus, the software will do everything for you. So it's going through all the focus procedure, and it does this in a few seconds. It's tuned, so you can see that now the light is green. So let's keep scanning again. Okay. Now, what we have to do, so we have the beam is focused. So we're gonna go for the easiest experiment. It's basically using the lowest dispersion. So if you click here, so basically open the filter dialog here, and you have the list of dispersions available. You already focused we added 1.5 dispersion enable, but just to show you how to change the dispersion here. And we're also using the biggest aperture. So we have two apertures available, ISNR, which is 5 millimeters. And in this particular case, we have 1 millimeter is the smallest aperture, but it would be called on high resolution. Depending on the model on the GIF, the smallest could be either 1 millimeter or 2.5 millimeters. Okay. So at this point, we just change the energy because we want to show you just a very quick acquisition. And I'm going to change it to 500. So if you change it to 500, it started from about 200. So it always gives like 10% of the field of view. So the all field of view with dispersion 1.5 is 3000 EV. Okay. So let's bump the exposure time to maybe like 5 milliseconds. And, the trick is, in this particular case, when you have to choose the right exposure time, you could use automated, or you can actually look at the highest energy edge, which is in this case the silicon case, which actually is nicely observable there. So we can use 5 milliseconds. Go on preview to get a little bit better quality image. Go to the array. Let's select an area. Let's do it this way. We're interested in this area. And we know that in the specimen there are, we could go on live mapping to begin with, but you can also control, the pixel size and everything. Let's go for about 7 angstrom resolution. And we use an exposure time of 5 milliseconds, which is the same one we checked earlier on. We can use live mapping. If you want to select live mapping, you can just click on live mapping. You can also go on the periodic table and select all the elements that belong to this specimen, or you can open like a saved recipe here. We have a lot of already prepared for a different specimen. Okay. And at this point, so we are ready to go, and we say capture. And now the software should be able to collect spectra pixel by pixel and process the data and generate elemental maps. So we already found titanium. We found nitrogen in there. Nickel very soon. Silicon, there's quite a lot of silicon in the specimen. So we managed to find all these elements here. So we know where we have nitrogen. We found like a small amount of titanium, silicon pretty much everywhere. There's like oxygen in the specimen, also germanium as well. So nearly done. Done. So the software now is going to process the data further, and it's going to make sure to keep it the best possible quality maps. So at this point, we can stop for this session, and then I will continue on the next module.